In this video, we'll learn about titrations and learn about the different types of titrations that can occur. And we'll learn how to do stoichiometry calculations involving titrations. So a standard solution is a solution of known concentration, and it can be used to find the concentration of an unknown solution. And this is done using titration. So in titrations in chemistry, we use a variety of different tools. Each one serves a purpose. Remember, we're trying to make sure that our measurements are as precise as possible. So to prepare our solution, we used our volumetric flasks. We may have used a graduated cylinder to measure out some water. This is called an Erlenmeyer flask, also sometimes referred to as a conical flask. This is what you will do your titration in, or you'll release your solution into here. A beaker is something that you would collect a large set of stock solution, but this is not something that you would use for precision measurements, nor is the Erlenmeyer flask. This one's a bit more precise, but to be absolutely precise, when we need to titrate a certain volume, we would take one of our pipettes and pipette that into here. And then this is known as a burette, and it is extremely precise, and you can release small amounts of solution into the Erlenmeyer flask, and that we will be using for our titration. So to perform a titration, you would fill the burette with the standard solution, so the one that you know the concentration of, and then you're going to place a set volume of the unknown solution in the Erlenmeyer flask and add an indicator. So an indicator will change color when you reach a certain pH. It will help you know if your reaction has completed. And then you're going to add small bits of the standard solution to the flask, swirling between additions until the end point is reached. And you'll repeat the titration several times and take the average, because it is very difficult to reach the correct end point, because the indicator will change color in an instant, and you may have added a drop too more or too little. So to do multiple titrations would be best. So again, this is another way of looking at that. So you would make a standard alkali solution accurately and pipette, for instance, 25 milliliters of that into your flask. And then you will put acid into the burette, read the starting value. You'll run acid into the flask until the indicator just changes color. You'll read the burette again and then wash out the apparatus and repeat several times and take the average. So we'll take a look at our first example. So 15 milliliters of hydrochloric acid neutralizes 20 milliliters of 0.212 mole per liter of sodium hydroxide. What is the concentration of hydrochloric acid? And just as a note, these square brackets indicate concentration, so be able to recognize that. And if you had HCl in here, it would mean the concentration of HCl. So first thing you need is your balanced chemical equation. So HCl plus NaOH makes NaCl and H2O. This reaction is balanced. Everything is operating in a 1-to-1 ratio. So we'll write down the information that we know. So we know that we have 0.12 moles per liter of NaOH. And we had 20 milliliters of that. We also have 15 milliliters of the hydrochloric acid. So first thing we need to do is convert this to liters and then find our moles. So this is equal to 0.020 liters. So our number of moles, remember moles is equal to C times V. So these, because we're doing concentration, it's not divide down, multiply up this time. We just have to be mindful. This is a nice organizer, but remember C equals N over V. So to find our moles, it would be C times V. So 0.12 times 0.02. 0 is 0.0024 moles. Now remember, it's a 1-to-1 ratio. So this is also going to be 0.0024. And we need to now, to go up, we're going to divide. So we're going to divide here to find our concentration. But first we have to convert this to liters. So divided by 0.015. So the concentration of hydrochloric acid is 0.16 moles per liter. Our next example, we're being asked to find out what volume of 0.3 moles per liter of sulfuric acid is needed to neutralize 40 milliliters of 0.570 moles per liter. So we need to find the volume this time. So let's look at our equation, make sure everything is balanced. We have one sulfate, one sodium here. So we need to put a 2 here. And then that's going to make us have 4 hydrogens and 2 oxygens. So we need to put a 2 here to balance this side out too. So now we have 4 hydrogens, 2 sodiums, 1 sulfate, 1 sulfate. So remember, I'm just going to put the coefficient 2 there so we remember to deal with that. So we have 0.57 moles per liter and 0.30 moles per liter. And we have 40 milliliters, which is equal to 0.040 liters. So we'll find our moles. So 0.0228 moles. But remember, we're going to divide by 2, multiply by 1. So our number of moles of sulfuric acid is 0.0114. Then we're going to figure out our missing value. So V, remember from our relationship, T equals N over V. So it's going to be the moles divided by the concentration to find the volume. So divide that by 0.3. So our missing value is 0.038 liters, which is 38 milliliters. So you'll notice that it's almost the same amount of volume that's required to neutralize the sodium hydroxide. And the sodium hydroxide was almost twice as much in molarity or concentration as sulfuric acid, but because sulfuric acid has 2 hydrogens to interact with each hydroxide, you don't need as much. It's called a diprotic acid, and we're going to learn that a little bit later. So now we're going to learn about back titration. And back titration is used to analyze impure substances, and it's used when one of the substances is insoluble in water but will react with an acid. So sometimes one of the things you're reacting is a component of a larger substance. So for instance, in one of the prescribed practicals that we will be doing, we'll find out that we have to do a back titration to find out how much calcium carbonate is in an eggshell. So what you do is you react your unknown substance with a set volume of excess acid. So you react it with an amount of acid that you know will react with it, but still have leftovers of acid. Then you're going to take the remainder to perform a titration with a known base, so a standard base solution, to determine the amount of acid that's still left over. And then you'll perform stoichiometry to determine the amount of the substance that you have. So this is an example that we find in the cognitive textbook. So it states, a student carried out a back titration to determine the mass in grams of calcium carbonate present in a 0.125 gram sample of eggshell. The eggshell is reacted with 100 centimeters cubed, or 100 milliliters, of 0.100 moles per liter of hydrochloric acid. The excess hydrochloric acid was then titrated with 0.5 mole per liter sodium hydroxide. The average sodium hydroxide titer was 16.06 centimeters cubed, or 16.06 milliliters. Calculate the mass of calcium carbonate in grams present in the eggshell. So first off, we'll put our information that we know. So we know that the concentration of sodium hydroxide is 0.500 moles per liter. We know that our volume was 16.06 milliliters. That's equivalent to 0.01606 liters. So we multiply together, if we remember our concentration formula. So C equals N over V. So to find moles, it would be C times V. So that is equal to 0.00803 moles per liter. And remember, our ratio is 1 to 1. So the moles of hydrochloric acid is also the same, 0.00803 moles per liter. The next thing we have to do is figure out how much hydrochloric acid reacted with the shell, because that will help us figure out how much of the shell reacted. So the first thing we need to know is how many moles we started out with. So our initial amount, remember, so we'll do N equals C times V, and we had 0.100 moles per liter hydrochloric acid, and we had that in 100 milliliters, so 0.10 liters. So that is equal to 0.010 moles. So to figure out how much reacted, we have to subtract our amount that reacted with the sodium hydroxide. So the amount that reacted is equal to 0.010 minus 0.00803. So that's equal to 0.00197 moles. So this is how many moles of hydrochloric acid reacted with calcium carbonate. So finally, we need to find out what mass of calcium carbonate reacted, and then the moles from the moles. So we have our moles of hydrochloric acid that reacted was 0.00197 moles. And if we look at our balanced chemical equation, you have two hydrochloric acids reacting with every mole of calcium carbonate. So we need to divide our number in half. So that is equal to 0.000985 moles. You could put that in scientific notation if you wished. Then we need to multiply by the molar mass of calcium carbonate. So that's calcium plus 1 carbon plus 3 oxygens, and that's equivalent to 100.09 grams per mole. Multiply those together, and you end up with a mass of 0.0986 grams. So that's how you do a back titration. So then if we want to find out the percent composition of calcium carbonate in the eggshell, you would do the mass of calcium carbonate over the total mass of the eggshell times 100. And if you remember, the mass we just found out in the last example was 0.0986 grams, and the mass that we started with originally was 0.125 grams. So, and we're going to multiply that by 100. So that's equal to 78.9%. So almost 80% of the eggshell is calcium carbonate.